Case-based reasoning, CBR, developed in 1982 by Roger Schank and Robert Abelson, is an AI method that is deceptively simple, yet extraordinarily powerful. Its genius lies in capturing and predicting complex behavior patterns, without the need to break them down into individual components. CBR is especially powerful for complex human decisions. Today, we'll see how this method can enable a human-level decision algorithm for guiding an autonomous medical evacuation aircraft. This aircraft's mission is a life-critical rescue of wounded personnel from an active combat zone. Human experts are not systems of rules, they are libraries of experiences. This fundamental insight is what drives case-based reasoning. Experts often rely on past cases when making decisions. Traditional rule-based systems are challenged by complex scenarios. CBR, on the other hand, provides solutions based on past, similar cases, rather than rigid rules. Consider medical evacuation, one of the most dangerous helicopter pilots' missions. The image shows a Vietnam War-era combat evacuation scenario. Thousands of similar evacuations have been carried out by helicopters over the years. Recently, a dedicated rescue UAV has begun its development as a vehicle that is a perfect solution for this dangerous mission. The clear advantage of an unmanned vertical takeoff and landing aircraft over manned helicopters in such dangerous missions is obvious. But a critical challenge remains, providing this UAV with the ability to perform complex decisions, all on its own, decisions that are critical to the success of the mission. The main decision, that could turn to a life or death situation for the evacuee, is whether to continue the final approach into the landing zone, or abort the mission in case the conditions at the objective are too dangerous. It should be mentioned that due to possible communication limitations and the potential need for radio silence, the ability of the UAV to contact its base for guidance may not always be an option. Therefore, we must find a way to equip the UAV's mission computer with autonomous decision-making capability, sometimes under extreme conditions. Naturally, defining the requirements, or what the UAV's computer must consider, is the first stage in building any such system. Luckily, this is not too difficult a task, because we believe these are the same factors that rescue helicopter pilots consider today. So, following discussions with pilots and medics with extensive experience in this mission, we have come up with 14 main parameters that govern the decision whether to continue the approach or abort the mission. These range from objective measures such as density, altitude, temperature, or fuel remaining, and all the way to human-related factors like patient condition, crew abilities, and also some apprehension or even fear of mission failure. It should be mentioned that while it is extremely rare for pilots to unjustifiably abort a rescue, when such an abort is justified, the decision to abort is the more difficult one for the pilots, compared to continuing into harm's way, doing what they were trained for. At the bottom of the screen are the parameters arranged as a vector. Each parameter represents a critical decision factor which could tip the scale. Environmental conditions like wind and visibility, operational factors like fuel and sensors, threats like missiles and ground fire, and as mentioned, human factors including patient condition and the pilot's subjective judgment. As part of the CBR procedure, we collected and cataloged past missions to illustrate how the system works. Here is a sample of 8 cases from past evacuations, arranged in the same parameters vector format as we defined. The pilot's final decision is included as the last element in each of the vectors. We are showing 8 past missions here just to demonstrate how CBR works. In practice, you should always try and use as many as you can get your hands on. The more cases there are, the more reliable the mission computer's decision will be. That said, we will see in a moment that CBR can deduce preferred actions from any number of past cases, even just a handful, unlike neural networks that need thousands of cases as a minimum to learn effectively. This gives CBR a huge advantage in learning from past experience. To illustrate how this vector portrays a real scenario, let us look for example at case number 3. Moving from left to right, we can see that the helicopter had 25% reserve power, because it needed to lift just 75% of its maximum allowable weight. We also read that it had sufficient fuel. These are therefore highlighted in green. Wind conditions were marginal, hence the yellow highlighting. Temperature was at ISO conditions, which means 15 degrees Celsius at sea level, perfect for producing high power and lift. Terrain altitude was 1,700 feet, which already introduces some air density related power losses, so it's highlighted in yellow. Ground slope, surface condition and sensors health are all in the green. Visibility is marginal, so marked in yellow. There are no mechanical issues, but light ground fire is reported. However, rescue helicopters have some armor plating and can take that fire, so we're still in the green here. No missile warnings and no major obstacles, so that is also green. The patient condition is reported by the ground crews as being severe. This information is known, continuously updated by the ground crews, and transmitted to the aircraft whether it is a manned helicopter or an unmanned vehicle. And we can see that the pilots decided to continue their approach. As for our UAV's specific conditions today, here is today's vector of parameters, based on a survey of the landing zone, as sensed or estimated by our UAV approaching the area, and already having it in sight. The question mark represents of course the yet unknown decision our mission computer will have to make: continue the approach, or abort. Soon the computer will run the CBR analysis, and we will have an answer. Before we move to extract the best course of action for today, it should also be mentioned that the CBR method allows us to assign weights to each parameter, based on their relative importance to the mission outcome. These weights help the algorithm focus on the most critical factors. Language processing tools can now determine which previous case our current parameter vector most closely resembles, while maintaining symbolic definitions. However, the fastest approach for finding vector similarities is converting each symbolic parameter to numerical values. This conversion assigns each symbolic parameter a number between 0 and 1, representing the severity of its condition. As an example, we see at the bottom of the screen how this was done for the ground fire parameter. This scaling simply transforms qualitative assessments into quantitative ones, while preserving the relative relationships between different severity levels. It should be mentioned that this order can be reversed, as long as the changes, both in the wording and their equivalent values, remain either monotonously increasing, or monotonously decreasing. With everything now being numeric, several data science approaches can compute vector distances to assess similarity levels. Here we will employ a simple but effective tool, the local global weighted Hamming classifier. This classifier has two stages with different equations: local similarity for specific parameters, and global similarity for overall case comparison. Here is an actual similarity calculation between our current scenario and the first historical case. We first apply the local similarity, first equation, and then calculate the global similarity, second equation. Here we show how the equations are applied in the case of the first vector. Once done for all the vectors, we have values for the final similarity between our current state and each one of the past events. As we can see, case 3 has the highest similarity score of 77%, making it the closest match to our current circumstance. Now, we look at the pilot's decision. Here, we can see that they elected to continue the approach. Again, we're not trying to build and run an intricate AI model to replicate their mental process. Instead, we recognize that they were the pilots back then, respect their decision, and learn from it. But is this enough for making a safe decision? Consider for a moment that instead of a computer, we had two pilots on board. An inexperienced pilot flying, and a seasoned instructor with thousands of flight hours, including 8 combat rescues under his belt. Even if this instructor keeps quiet, letting the young pilot make decision himself, this young pilot is likely to question the veteran. What would you do in our situation? Continue or abort? The veteran pilot, drawing on extensive rescue operations, would recollect a similar instance. And more than likely, advocate the same course of action he took back then. Would anyone think that the young pilot would do otherwise? Definitely not. Our UAV does not have any pilots to consult with. However, it has access to a large number of previous cases, and can identify the one that most closely resembles the current circumstance. So rather than attempting to emulate human cognition, an impossibly sophisticated analysis with limited time, all our mission computer has to do is follow what CBR identified as the most appropriate action, based on a human crew's previous judgment. But how do we know that a past judgment was correct? We will address this dilemma in a moment. In the meantime, let us show how CBR is able to catch even slight nuances in the historical cases, without even attempting to rebuild the intricate mental process that led to the pilot's decisions. Consider for example that our UAV receives an update during its approach. The wounded soldier has been stabilized, is no longer critical, and is now classed as medium condition. This parameter modification results in an immediate recalculation of all case similarities. With the updated patient condition, our similarity scores change dramatically. Now case 7 becomes our closest match with the highest similarity. In case 7, the pilot decided to abort the mission. Our algorithm now adopts this new decision, reflecting how reduced urgency changes the risk-benefit calculation. This dynamic adaptation shows how the algorithm responds to changing conditions, just as human pilots would. Notice a vicinity value of 77.8% between our UAV's current parameters vector and that of case 7. While we would certainly prefer a higher score, above 90 to 95% if possible, note that we have achieved almost 80% with just 8 previous cases. This in itself is a remarkable achievement for CBR. Before we move on, a note on the weights. These can come from 2 sources, either by interviewing seasoned rescue pilots for their preferred scale, or reconstructing the weights via machine learning with backpropagation. The machine learning method starts with random weights. We then iteratively test each historical case by hiding its decision and predicting it based on the most similar remaining case. We update the weights with each iteration to achieve the least prediction errors, until we converge on the optimal combination that best reproduces the pilot's decision patterns found in the historical data. Let us now answer the question: what if a past decision was wrong? The final column in the table shows the mission's completion status, demonstrating how different decisions led to different outcomes in past cases. Imagine that we are now at the stage of preparing the bank of previous cases for our UAV's mission computer. Sitting with experienced rescue pilots, we go over the cases one by one, and let the pilots tell us what they think. Looking for example at case number 8. One of the pilots notices that many of that day's parameters were in fact in the red. Still, the pilots decided to continue. A note attached to this case tells us, however, that this mission was unfortunately not completed. This is enough to have our pilots recommend to either remove this case from the list, or even better, change the decision retrospectively from continue to abort. This modification of course does not change what actually happened in the past, but the mistake that these pilots made can be used as a valuable lesson for our UAV to learn from. If it ever encounters similar conditions, it will abort the mission. Again, note that despite performing mathematical operations, we didn't try to quantify unmeasurable human factors like fear or courage. We took each pilot as a complete package. The algorithm completely adopted the pilot's decisions in the most similar cases, including their intuition, courage, fear, and sense of duty. In that, it fully captured their expertise, and is applying it to future situations. To sum up, case-based reasoning, invented in 1982, has seen widespread use over the years in decision-making under uncertainty. This includes, among others, safety systems, fault detection, maintenance, and medical diagnosis. In recent years, CBR is even developing strong synergies with neural networks, where each system benefits from the other's unique capabilities. More on that, perhaps in a future video.